The heart of an EV is the battery, and the battery war in recent years has long moved beyond the battle of chemical formulas, burning into a war of physical structural forms. Currently, the two biggest factions on the battlefield. On one side, Tesla betting on the cylindrical 4680. On the other, BYD is leading with the rectangular blade battery. This isn't just a simple difference in shape. This is a showdown of geometric efficiency. Today, we are not talking about blind faith. I will speak from the perspective of an electronics engineer, using 5 hardcore engineering dimensions to deconstruct the ultimate battle between these two top-tier structures. Point 1. Geometric fill rate. Round 1. Let's look at the most intuitive geometry. That is, who can utilize every bit of space in the battery pack? Think back to high school math. If you stuff a bunch of cylinders into a box, no matter how you arrange them, there will always be gaps between the cylinders. This is the geometric original sin of the circle. Although Tesla now uses structural adhesives to fill these gaps, structural adhesive does not store electricity. In contrast, the blade battery is a rectangular prism. A rectangular prism is a shape that can geometrically achieve 100% tessellation. Like books lined up one by one, there are almost no dead corners. This leads to a very interesting result. Although the blade battery uses lithium iron phosphate LFP, whose chemical energy density is inherently lower than ternary lithium, by relying on the geometric advantage of packing the box fuller, in terms of total capacity of the battery pack, it actually catches up with many ternary lithium solutions. This is a classic case of using engineering design to compensate for material shortcomings. Point 2. Thermal management. Round 2 is what we electronics guys care about most: heat dissipation. The 4680 uses side serpentine cooling tubes. Please note, cylinders can only contact cooling tubes on their sides, and this is a curved surface contact. The contact area is actually limited. So how does the blade battery do it? It takes that largest side surface area and pastes it entirely onto the liquid cooling plate. If you've ever assembled a computer, you know, this is like a CPU cooler. The 4680 is like using heat pipes for contacts, while the blade battery is like using a huge vapor chamber for direct contact. Physically speaking, the heat dissipation efficiency of blades' large surface contacts is inherently superior to the cylinder. This means that during fast charging, the internal temperature difference of the blade battery will be smaller. This is definitely a plus for battery life. Point 3. Internal resistance and electrical path. Round 3, we dive deep inside the cell to look at electrical performance. Here I want to give a thumbs up to 4680's tabless technology. Traditional cylindrical batteries are wounded very long, so current travels a long way, causing high internal resistance. But 4680 turns the tab into the entire cross-section, turning a narrow, winding path into a superhighway. Internal resistance drops significantly. This allows it to easily support furious power output. But the blade battery is not weak either. It uses stacking technology. Simply put, it stacks many layers of positive and negative electrodes in parallel. This also drastically reduces internal resistance. So on this point, I think it's a draw. Whether it's tabless or stacking, both technologies have eliminated the high internal resistance bottleneck of traditional batteries. Bottleneck. They represent the pinnacle of current human engineering. Point 4. Structural rigidity. Round 4. The battery is not just a battery anymore. It is now part of the car body. Let's look at the data. BYD seal model, because it uses CTB technology, which means using the long strip blade battery as the structural I-beams of the car body. Its whole vehicle torsional stiffness reaches 40,500 Newton meters a deg. This number is exaggeratedly high, already at the level of million-dollar luxury sports cars. While the CTC technology adopted by Model Y has a stiffness of about 21,700 Nm deg, although also excellent in absolute rigidity. The tightly packed, honeycomb-like structure of the blade battery pack does indeed have an advantage in torsional resistance over the cylindrical cluster. And one more thing, because the blade battery is flat, it allows the chassis to be made thinner. Every millimeter saved here. There is precious headroom for the passengers inside. Point 5. Manufacturing and reality. Finally, we return to the cruel reality: mass production difficulties. The highlight of 4680 is the dry electrode, which is a nano-level processing challenge. The difficulty is very high, and current yield rates are still struggling to ramp up. This is also why the early 4680 production capacity was limited. It is betting on the future ceiling. Meanwhile, the blade battery stacking process, though complex, has been refined in the electronics industry for many years. Belonging to a mature manufacturing process, its yield is high and cost control is excellent. This is why BYD can push costs so low. It earns profits from the present. Conclusion: to summarize today's analysis, 4680 is the ultimate in engineering thinking. It uses the most complex processes to challenge physical limits, all in pursuit of extreme performance and fast charging. The blade battery is a victory for product managers' thinking. It uses the most clever geometric structure to solve the most practical space, heat dissipation, and cost issues. There are no losers in this war of geometry. They are both using different ways to tell us that the EV revolution has just begun.